Alright, in this video we're going to be looking at 6.1, the vector fields. So this will be the first of, I believe, 2 videos for section 6.1. And what a vector field does is it assigns each point a vector. So example for vector field is you have a vector field in the plane. F of x, y is equal to mi plus nj, or m and n are functions of x and y. Or if you're in space, f of x, y, z is equal to m sub I plus n sub j plus p sub k, where m, n, and p are functions of x, y, and z. So we're going to take a look at an example here. Our vector field f of x, y is equal to yi minus xj. We're going to sketch the vector field using the following points. So you have 0, 0, 1, 1, negative 1, 1, negative 1, negative 1, 1, negative 1, 2, 2, negative 2, 2, negative 2, negative 2, and 2, negative 2. So we're going to go ahead and set up the rest of our table. So our function f of xy is equal to yi minus xj. So at the point 0, 0, we have the 0 vector. At the point 1, 1, we have the point 1, negative 1. Okay, so we'll draw that vector. And at the minus 1, 1, we will have the vector 1 and positive 1. We'll draw that vector in there. At the point negative 1, negative 1, we will have the vector negative 1, positive 1. And at the point 1, negative 1, we have the point negative 1, negative 1. Okay, so based off of those 4 points, really, the ones with the 1, looks like we have a clockwise rotation there. And let's go ahead and look at all the variations of 2 and negative 2 paired together. Okay, so at 2, 2, we're going to have the point 2, negative 2. Okay, so at 2, 2, we have the vector 2, negative 2. At the point negative 2, 2, we have the vector 2, 2. At the point negative 2, negative 2, we have the vector negative 2, 2. And at the point negative 2, at the point 2, negative 2, we have the vector negative 2, negative 2. Okay, so it looks like we have more of that clockwise rotation. I believe this vector field is also sketched in your textbook, and they show that maybe this vector field kind of shows a rotation of maybe water draining down the sink, or maybe a hurricane or something like that near the eye wall there as our rotation. Let's do one more example of sketching a vector field. Okay, so we're going to sketch the vector field determined by f of x, y is equal to yi. So the j component is going to be 0 for the entire vector here. For each vector in the vector field. So let's go ahead and do an xy, and f of xy is equal to yi. And then we're just going to pick some points. So we'll start with the origin. And at the origin, we're going to have the 0 vector. At 1, 1, the only thing that matters is the y coordinate. Okay, and so it's going to be yi, so 1, 0 as your vector. If we look at 2, 2, the vector is going to be 2, 0. If we look at 3, 3, the vector is going to be 3, 0. If we look at negative 1, again, it's that y coordinate that matters. It's going to be a vector of negative 1, 0. Oops, we got an extra angle bracket there. What else do we got? Let's look at negative 2, negative 2. Again, the y coordinate is going to determine the vector, so it's going to be the vector negative 2, 0. Negative 3, negative 3. So we're going to have the vector negative 3, 0. And we got an extra angle bracket there. Okay, so let's go ahead and sketch some of those vectors. So the 0 vector. The vector at 1, 1 is going to be 1, 0. Okay, the vector at 2, 2 is going to be the vector 2, 0. The vector at 3, 3 is going to be the vector 3, 0. Okay. The vector at negative 1 is going to be the vector negative 1, 0. The vector -2, -2 is going to be the vector -2, 0. And the vector at -3, -3 is going to be the vector at -3, 0. So it appears as you go up and you increase in terms of y or decrease in y, the absolute value of the y as that gets larger, the larger your vector is going to be. Let's do a couple more points. So let's look at 1 and -2. So that's going to give us the vector -2 and 0. Okay, so there's the vector there. What about the point 2, 5? That would give us the vector 5, 0. So do 5, 2, and so it's going to give us a vector 5, 0. This should be more of an angle bracket here. All right, -3 and 4. That point will give us the vector 4, 0. So there it is. Okay, and then you can keep going, so we kind of have a good representation of what this vector field looks like. So it's completely dependent on the y value in terms of the length of the vector. Okay, so let's move on to a little bit more for this video. And so we're going to look at conservative vector fields. So we say a vector field f is called conservative when there exists a differentiable function, lowercase f, such that the vector field f is equal to the gradient of lowercase f. The function lowercase f is called the potential function of f. So f of x, y, that's your vector field function. That's going to be equal to the gradient of lowercase f, or in 3 dimensions, f of x, y, z, your vector field, is equal to the gradient of lowercase f. Okay. For f of x, y is equal to m sub I plus n sub j. This is going to be a conservative vector field if and only if the partial derivative of n with respect to x is equal to the partial derivative of m with respect to y. So if that condition is met, then we have a conservative vector field. So let's look at an example of that. Okay, so example, we're going to verify that the vector field determined by f of xy equals 12xyi plus 6 times x squared plus yj is conservative. If the vector field is conservative, go ahead and find the potential function of f. Okay, so what we want is the gradient of this function f, which would be the partial derivative of f with respect to xi plus the partial derivative with respect to yj. We want that to be equal to our vector field, which is 12xyi plus 6 times x squared plus yj. Okay, so our function m is going to be the I portion of our vector field. So that's going to be 12xy. The partial of m with respect to y is going to be 12x. The n function is going to be the 6x squared plus y. The partial of n with respect to x is going to be equal to 12x. So those match, and so this means that our vector field is a conservative vector field, which means the previous theorem says that we have a potential function. Okay, and so that potential function is going to be kind of like an antiderivative. So the gradient is kind of like your derivative operator. So the derivative of your antiderivative is going to be the original vector field. So let's go ahead and find our potential function. So f of xy is going to be equal to the integral of m dx, okay, which is going to be equal to the integral of 12xy dx. So that's going to be 6x squared y, and then plus some function g of y. So we want this to work so that when we take the gradient, we would get the 12xyi. And then we'll go ahead and do the same thing. F of xy will also need to be equal to the integral from integral of n dy, which should be the integral of 6 times x squared plus y dy. so that we will, when we take the gradient, we will get the 6x squared plus y for our j component. So when we integrate that, we're going to have 6 times x squared y plus y squared over 2 plus your constant of integration. It's going to be an h of x, a function of x. Okay, so that's going to give us 6x squared y plus 3y squared plus a function of x as our constant. All right, so our potential function, in order for this to work, we need the 6x squared y, okay, and so that's required for both the gradient to give us the 12xyi, and then also part of it is for the 6x squared for the j, and then we need the 3y squared, we need the derivative of that so that we can get the y in the j component. Okay, so we'll need that as well, and then we'll have our constant of integration there. Okay, you can think of this g of y as this 3y squared here, and then possibly another constant, like plus 5 or something like that. Okay, so we have our potential function. Later on, that's going to be important to us when we get into looking at conservative vector fields and some theorems with line integrals, which we'll get into a little bit later on. So it kind of serves as like an antiderivative, and there's a connection with this with the fundamental theorem of calculus, part 2. Okay, so let's go ahead and actually verify that this is the quote-unquote the antiderivative of our vector field. So we would take the derivative of the antiderivative, and we should get back to the original function. In this case, we take the gradient of our potential function here. Okay, so you're going to take the derivative of 6x squared y plus 3y squared plus c with respect to x. Okay, so partial derivative would be 12x y, the 3y squared and the c, they don't have any x's in there, so they're treated as constants when we take the derivative, and they become 0. Okay, so the gradient gives us a 12xyi. Okay, now when we take the partial derivative of our potential function with respect to y, we're going to have 6x squared plus 6y, and then the derivative of the c would be gone, it'd be 0. Okay, and so then we have plus the 6x squared plus the 6y, and that's our j component. Okay, and then we can go ahead and rewrite that as 12xyi plus 6 times the quantity x squared plus y, j. And so we have verified that we did find the potential function, because when we find the gradient of the potential function, that gives us our vector field. Okay, all right, so that's it for this video. I have one more where we'll look at a little bit of the curl and also the divergence of a vector field, and also we'll do another example of what a conservative vector field would look like in space as opposed to just in the XY plane. Okay, so stay tuned the next time.